Very good afternoon to one and all. So up to yesterday's session, we tried to cover the revision of our fourth unit. Okay, we already completed a revision of fourth unit in up to our yesterday's session. Okay, from today onwards, we are going to discuss about a revision class of third unit. So this is the very smallest unit when compared to all the remaining units. So this unit is very easy to get 15 out of 15 marks. Okay, listen carefully. Okay, now coming into this third unit, it related to sampling theorem. Okay, now today we are going to discuss about revision class 1. It related to unit 3. Today we are going to discuss about the following two topics. Number one, sampling process. Number two, sampling theorem. Okay. Now, what is meant by sampling process? What is meant by sampling process? Okay. Here, we all are know. Basically, there are different types of signals are there. There are different types of signals are there. Different types of systems are there. But here only we try to focus continuous type signal and continuous type systems. Okay. Because around and surrounding us, whatever the available signals are there, whatever the available systems are there, all the available signals and systems are in continuous in nature. Okay, around and surrounding us, whatever the available signals are there, whatever the available systems are there, all the available signals and systems are in continuous in nature. Okay, now recently we all are need a digital platform, a digital signals. So that's why all the available signals in continuous time signals are converted into discrete time signals. Okay, the another name of discrete signal is called as a digital signal. Another name of discrete signal is called as a digital signal. And another name of continuous time signal is nothing but analog signal. Okay, so we all are know around and surrounding us, whatever the available signals are there around and surrounding us, all the available signals and systems are in continuous in nature. Okay, we need a digital information or a digital data. So in order to convert the available continuous time signal into discrete signal or digital signal. Okay, the another name of continuous signal is called as analog signal. The another name of discrete signal is called as the digital signal. Okay, now what is the sampling process? Sampling process means in order to convert the available continuous time signal is converted into discrete signal or a digital signal. In order to convert continuous time signal into discrete time signal is called as sampling process. Okay, technically we called as coding. Technically we called as coding. Okay, here the intention is very simple. Here it is a system amma. Here we are providing the input. The input is there in terms of continuous time signal. Continuous time signal. Okay, this device or the system is used to convert continuous time signal into discrete time signal. Discrete time signal. So in order to convert continuous time signal into discrete time signal is called as sampling process. Technically we called as coding. Technically we called as coding. And now in order to convert discrete time signal into continuous time signal. In order to convert discrete time signal into continuous time signal. In order to convert discrete time signal into continuous time signal is called as data hold. Is called as data hold. Technically we called as decoding. Technically we called as decoding. So the point is very simple, Amma. Sampling process means we all are know in around and surrounding us, whatever the available signals are there, all the available signals are in continuous in nature. Here, it is a continuous in nature. Okay. Now, this continuous time signal is converted into discrete time signal. Discrete means I try to represent dotted line here, whatever the signal is. In the dotted line, what we are getting here, output here. But signal into is called as sampling process. Technically, we called as coding. In order to convert discrete time signal into continuous time signal, here quite opposite. In order to convert discrete time signal into continuous time signal is called as data hold. Is called as data hold. Data hold. This is called as decoding. It is called as decoding. Okay. How to convert continuous time signal to discrete signal? Here, simple thing. Now here, try to understand, Amma. Now here it is called as a continuous time signal. We try to represent anything, either x of t or m of t, whatever alphabet we are using. It is a continuous time signal. In order to convert, here we are getting x of n. Okay. Now, when the input is here from this position to this position, the available signal is continuous. Okay. Now, from this time period to this time period, we are getting continuous signal. Now, how to convert continuous time signal to discrete time signal? Now, with the help of a simple switch. Here, sampling process means it is simple switch. Here, it is a simple switch. It is a simple switch. Okay. The switch is called as sampler. The switch is called as sampler. It is denoted by del of t. Denoted by del of t. It is a sampler. Okay. It is like a switch. Now, it is a continuous signal. It is a switch. Now, when a continuous signal is given to the sampler, now the sampler is acts as a switch. Now, the switch having two modes of operation. One is when switch is in on, another one is in when switch is in off. Okay, when switch is in on, we are getting corresponding output. For example, in this time, when the switch is on, here switch is on means here we try to generate pulses. Here we try to generate okay. Here these are called as pulses means in this time when switch is on. In between pulse to pulse, some gap is there. In this time when the switch is off. Okay, there are two things. Number one, when switch is on, switch is off. Switch is on means we are getting pulse. When switch is off means we are not getting any pulse. That's the difference. Okay, here the simple thing. Okay, wait a second. I try to convey. Here, the point is here it is called as a continuous time signal. It is called as a continuous time signal. Okay, now in order to convert the continuous time signal to discrete time signal with the help of a sampler. Sampler means it is acts as a switch, simple switch. Okay, it is acts as a switch. Okay, this is denoted by del of t. Now, here when the switch is on, we try to generate pulse. Pulse is generated means switch is on and if pulse is not generated means switch is off. If switch is on means on. In between gap is there. In this mode, when switch is off. In this mode, switch is off. Pulse is generated, that is switch is on. Pulse is generated, switch is on. Okay. Now the sampler is used to. Okay, when the switch is on or off, when the switch is on, we try to generate pulses. Now, when the switch is on, we are collecting the corresponding output. In this time, switch is on, we are getting output. In this time, when switch is on, we are getting output. This is called as a discrete signal. Okay, in order to convert continuous time signal to discrete time signal through device is called as sampler. This process is called as sampling process. Okay, here we are providing any signal, continuous time signal here. Okay, it is connected to switch. Now the switch is used to turn on here. Based upon the availability of input. Here the availability of input is 0 to, for example, this is called as 100. That means the switch is turn on from 0 to 100. At 0 switch is on. At a 10 switch is on. At a 20 switch is on. 100 we try to turn on the switch. Between 0 to 10 switch is off. The corresponding output here. When at 10 the switch is on, we are getting corresponding output. At 20 the switch is on, we are getting corresponding output. This is the process. Okay, this question has 70. Okay, listen carefully. For example, signal here. It is continuous time signal. Okay, from negative here minus 10, here this value is positive 10. Okay, now I try to consume signal. The signal is here. Okay, from 1 to 10, this signal is there. These two are continuous. These two are continuous. Okay, now in our intention is very simple to convert continuous time signal to discrete time signal with the help of sampler. Sampler means it is actually a switch. Now switch intention is it is used to generate the pulses. When the switch is on, we try to generate pulses. So when the switch is on to generate the pulses for every time period t, from what about the available input signal? It is there from minus 10 to 10. Now the switch is on from minus 10 to plus 10. Minus 10 onwards, minus 10, minus 9, minus 8, up to 1, up to 10. So here the sampler relation is very simple. It is used to generate the samples for minus infinity to plus infinity. But we try to generate the samples to turn on the switches based upon the available input. Available input is negative to positive. From negative to positive, we try to generate the samples. Now here, the input is there only positive. So the sampler is used to generate the samples only for positive from 1 to 10. Okay, what is the reason why we are not generating negative values here? Because when the available input is only positive, no need to turn on the switch. Okay, to turn on the sampler to generate the samples, actually it starts from minus infinity to plus infinity for every instant of time t. Okay, but the available input is minus to plus. From minus to plus, we try to generate the samples. The available input is only positive. We try to generate the samples for only positive. Okay, now we are getting corresponding output. So whatever the output we are getting here, so that is called as x of n. Whatever the input signal is there, I try to represent a dotted line here. Okay, from here, when switch is on, we are getting corresponding output. Here, when the switch is on, we are getting corresponding output here. Now here in this waveform, only positive we are getting output here. Okay, any doubts, Amma, regarding to sampling process? Anybody having any doubts? Anyone? Do you understand? Okay, so listen, the sampler means it is used to generate the samples. Okay, it is used to generate the samples from minus infinity to plus infinity for every instant of time t. Okay, for example, it is generated 0. Sorry, one pulse is generated 0, another pulse generated t. Okay, the next pulse generated 2t. Okay, that means the distance of each pulse is t and d. Okay, the capability of sampler is used to generate the samples from minus infinity to plus infinity. Minus infinity to plus infinity. But here the point is very simple. Okay, availability of input, we try to generate the samples. The availability of input negative to positive, we try to generate the samples also from negative to positive. Because in order to convert only positive, the samples are generated only positive. Because no need for the negative samples. Okay, the available input is only negative. We try to generate the samples in only negative because no need for the positive, because the continuous time signal is very negative. Okay, so this is the sampling process. Anybody having any doubts? Anybody having any doubts? Respond, Amma. Right. So that is the 8 marks question. Right, Amma. Amma, listen carefully, Amma. So this is a very, very important concept. Okay. So this question carry 15 marks direct question, Amma. 15 marks direct question. Listen carefully. Question is, explain the sampling theorem of low pass signals. Number 1. Second question, explain the sampling theorem of band limited signal. Band limited signal and low pass signal, those two are same, Amma. Sampling theorem of band limited signal or sampling theorem of low pass signal, those two questions are same. Okay, here try to understand sampling theorem of band limited signal or sampling theorem of low pass signal, those two are same. The weightage of this question is 15 marks. Okay, according to your syllabus copy, the syllabus had sampling theorem of band limited signal, graphical and analytical proof. Okay, Namma? So listen carefully. Band limited. One more theorem is the sampling theorem of band pass. That one is different. Okay. Here the theorem is sampling theorem of band limited signals or low pass signals. These two are same. Right. Coming to the sampling theorem, here once again we try to recollect the information from our first topic. It is called as input amma. We are getting the output. Okay. What is the need of sampling theorem? Here, once again, we all are know around and surrounding us, whatever the available signals are there, all the available signals are in continuous in nature. Okay. In order to convert the continuous time signal into our required signal, that is called as a discrete signal. Okay. The process by which to convert available continuous time signal into discrete signal is called as sampling process. How to convert continuous time signal to discrete time signal? Anybody guess? With the help of how to convert continuous time signal to discrete time signal? Anyone guess? How to convert continuous time signal to discrete time signal? Very good, Amma. Sampler. Okay. The sampler another name is also called as multiplier. Very good, very good. Sampler, by using sampler. Okay, sampler means it is acts as a switch. It is acts as a switch. Okay, the sampler is denoted by del of t. Del of t. Okay, the sampler intention is very simple. It is used to generate the samples from minus infinity to plus infinity for every period of time t. For every period of time t. Based upon the available input signal, the sampler is used to generate the samples. We are getting corresponding output. Okay. Now this is a simple story. Okay. Sampling process means to convert continuous time signal into discrete time signal. So continuous time signal means here the point is very simple. Throughout the period, the data or information is available. That is called as continuous time signal. Discrete time signal means only at particular instant of time only. Only at particular instant of time only. We are getting the output that is called as discrete time signal. Okay, only at particular instant of time only we are getting the data or information is called as discrete time signal. Okay, now so our concept is sampling theorem. Our concept is sampling theorem. Sampling theorem means here once again I try to convey. I want to consider, try to understand a concept, Amma. It is a continuous time signal, Amma. I try to consider this is a continuous time signal. Choice is yours. Okay, I try to consider this is a continuous time signal. Okay, it's a plus t and this is a negative t. Now, I try to convert continuous time discrete time signal with the help of a sampler. It is called as del of t. It is acts as a switch. Okay, the sampler is used to generate samples from available input to available starting end to ending end here. From here, I try to turn on the switch. Here, I try to turn on the switch. Here, I try to turn on the switch. I try to turn on the switch. I try to turn on the switch. Here, in every instant of time t, the switch is on. Okay, when the pulse is generated, means switch is on. When the pulse is not generated, means switch is off. Right. Now we are getting corresponding output here. It is called as n. It is called as minus n. It is called as x of n. Now whatever the input signal is there, I try to consider in place of input signal, I try to consider dotted line. I try to consider dotted line. Now from here, when switch is on, we are collecting the output here. We are collecting the output here. Here when switch is on, we are collecting the output here. When switch is on, we are collecting the output here. Similarly, the remainder. So here we are getting discrete signal. Okay. Now, in order to convert continuous time signal to discrete signal, this is called a sampling process. What do you mean by sampling theorem? Sampling theorem means in order to reconstruct the original signal. Here, original signal is called as continuous time signal. Okay. The first step is the continuous time signal is converted to discrete time signal. This is the first step. Second step is once we try to convert into discrete signal, this signal is used to reconstruct the original signal. Okay, now the continuous time signal is converted to discrete signal. Then this discrete signal is used to convert it into our original signal, that is continuous time signal, without losing any data or any information. Sampling theorem, that is called as sampling theorem. Okay, the point is very simple, Amma. Okay, here we all are know the continuous time signal is converted to discrete time signal. Okay, this is step number one. In step number two, once we are getting a discrete signal or sample output signal, now this sample output signal is used to construct the original signal, recover the original signal from this output without losing any data or any information, is called as sampling theorem. Okay, sampling theorem means we know the continuous time signal is converted into discrete time signal. Up to till now everything happy. Once we are getting a discrete time signal, this signal is used to reconstruct the original signal. Here the original signal is the continuous time signal. Okay, the discrete time signal is used to reconstruct the original signal without losing any information or any data, is called as sampling theorem. It's called as sampling theorem. Anybody having any doubts? Anyone? Do you understand related to sampling theorem? Okay, right? Once again I try to convey, because without having proper idea it is very typical to us. Okay, listen here. It is called as a continuous time signal, it is a discrete time signal. We all are know from continuous time signal is converted into discrete time signal. This process is called as sampling process. This process is called as sampling process. Now once we are getting discrete output, this discrete output is also be called as sample output, because this output we are getting through sampler, that's why it is called as sampler output. Sampled output, sampled output. This sampled output is used to reconstruct the original signal. Once we try to convert continuous time signal to discrete signal or sampled output signal, once we are getting sampled output signal, this signal is used to reconstruct the original signal without losing any information or data, is called as sampling theorem. Is called as sampling theorem. Sir, why is that? Why you said without losing any data or information? So listen carefully. Discrete time signal means the data is available only at particular instant of time only, but continuous means throughout the period is available. Now in order to convert continuous to discrete is one step, but discrete to continuous, in order to overcome all the gaps, whatever the gaps are there in this, here we try to fill here continuous without losing any data or any information. That is called as sampling theorem. Okay, I hope you understand. Now according to that, here the continuous time signal is called as, here the continuous time signal is called as original signal. The continuous time signal is called as original signal, original signal, and we are getting whatever the discrete output. Here whatever the output we are getting, this is called as sampled output or discrete signal. Sampled output or discrete output. Now here in this continuous time signal, the frequency is called as FM. This is called as original signal or continuous time signal frequency. In this discrete signal frequency is called as FS, sampling frequency. Okay, there are two frequencies are there. Original signal frequency is FM, fundamental frequency. Digital signal frequency is called as FS. In technically, F is nothing but frequency, and omega is also be called as frequency. Okay, F or omega, these two are called as frequency. F or omega. Okay, now here, now when the continuous time signal is converted to discrete time signal, once we are getting a discrete signal, that signal is used to reconstruct the original signal. Original signal is nothing but a continuous time signal. This signal is used to reconstruct the original signal without losing any information or any data. Without losing any information or any data, okay, is called as sampling theorem. Okay, now the original signal, the frequency is FM, and sampled output the frequency is Fs. Okay, what about the sampling theorem statement? Fs is greater than or equal to 2fm. Fs is greater than or equal to 2fm. Means Fs, that means sampling frequency of discrete signal is greater than or equal to twice of the fundamental frequency, that is frequency of original signal. Okay, now our intention is very simple. In order to convert original signal into discrete signal, and this discrete signal is used to convert original signal without sampling frequency is greater than or equal to twice of the fundamental frequency. Okay, the original signal is recovered from the sample output signal without losing any information or any data when sampling frequency is greater than or equal to twice of the fundamental frequency. Only this particular case only, we are converting original signal from sample output signal without losing any data or any information. Simple point, simple point. Okay, it's a simple logic or simple point. Okay, now once again I try to convey here. We know that, okay, I try to consider it is a signal that is called as x of t. Okay, this is a signal, it is called as x of t. Now with the help of sampler means it is as a switch. Okay, now the sampler intention is very simple. It is used to generate the samples for every instant of capital T. Okay, from minus infinity to plus infinity. But here, based upon the availability of input, we are considering a sample, right? Now we try to convert the output, it related to discrete output, or this also be called a sample output, because after sampler we are getting output called as sample output. Another name is called as discrete signal, right? So in this time we try to turn on here. I try to dotted line here. I try to get here and here and here. This is the discrete output. Now in this continuous time signal, the frequency is called as FM. In this sampling signal, the frequency is called as Fs or omega or F, whatever the option you are considered, whatever the option you opt. Okay. Now, here our topic is very simple. In order to convert continuous time signal, the continuous time signal is also be called as original signal. Original signal. This original signal is used to convert it. This original signal is converted into sampled output signal or discrete signal. Okay, through sampler. After that, this discrete signal or sample output signal is used to reconstruct the original signal. This output signal is used to reconstruct the original signal without losing any information or any data when the sampling frequency is greater than or equal to twice of the fundamental frequency. Twice of the fundamental frequency. This is called as sampling theorem of low pass signal or sampling theorem of band limited signal. Okay, so all the available signals are in continuous in nature, amma. We need a digital, so the available signals are called as original signals. The original signals are converted into our required digital signal through sampler. The sampler is used to generate the samples for every instant of time t. Once we are getting a sampled output, now this sampled output is used to reconstruct the original signal without losing any information or any data when sampling frequency is greater than or equal to twice of the fundamental frequency. I already told you the frequency of original signal is called as FM, that is fundamental frequency. The frequency of discrete signal is called as sampling frequency. Okay, now in this particular case only, we try to convert, we have to convert the original signal, we try to reconstruct the original signal from sampled output signal or discrete signal when Fs is greater than or equal to twice of the, twice means 2, twice of the fundamental frequency. So this is the statement of sampling theorem. Anybody having any doubts? Do you understand? Anyone having any doubts? Do you understand? Okay, Amma. Amma, if anyone having any doubts, feel free to ask me. Okay, so in this revision session also, so I try to explain same way from our starting classes. Okay, so I never skip any matter, I never skip any point to you. Okay, if anybody having any doubts, feel free to ask me. Right now, here once again, it is a continuous time signal. It is a sample. I already told you. It is a sample output. Sample output signal is also be called as discrete signal. Okay, sir, you told me this is a discrete signal. Sir, why it is called a sample signal? It means after the sampler we are getting the output that is called a sample output signal. Okay, this is the story. Right. Yeah. Once again, same story. It is a continuous time signal. The sampler is acts as a switch. It is used to generate the samples from minus infinity to plus infinity. For every instant of time t, we are getting corresponding output. Okay. Now, let's say one more example. Now let us consider a continuous time signal. Okay. Now here the point is very simple. Listen carefully. Whatever the signal, whatever the signal we are considered, whatever the signal we are considered, okay, that signal is a band limited signal. That signal is a band limited signal. So listen carefully. This word is very, very important. Okay, sampling theorem of low pass signal or sampling theorem of band limited signal. These two are same. Okay. Now here, whatever the continuous time signal you are considered, okay, that signal is a band limited signal. That signal is a band limited signal. Okay. Now here, this continuous time signal is converted to discrete time signal through switch or sampler. Through switch or sampler. Okay. Now we are getting sample output. Sample output, another name is called as discrete signal. Simple and sir, what is the reason why you are called as sample signal, discrete signal? Means I said clearly, after sample we are getting the output. That is called a sample output. Right? So here, this is the story. And moreover, the time interval between any two successive samples, the time interval between these two samples or these two samples or any two samples is called as sampling interval or sampling period. This is very, very important point. Okay, the time interval between any two samples, okay, when we are providing a continuous input through the sampler, we are getting the discrete output. In this discrete output, in between the time period between any two lines, that is called as sampling period. Okay, that is very, very important. I already told you the continuous time signal is a band limited signal. Right. Now, here I try to consider any shape of a continuous time signal. I try to consider any shape of continuous time signal. Here I try to consider. Any shape of a continuous time signal. I already told you the continuous time signal is a band limited signal. So the name itself, here the name is itself sampling theorem of band limited signal. Okay, so it is a band limited signal. Okay, now it is a band limited. Now we know that Fourier transform. The Fourier transform intention is the available input is x of t. Now x of t is converted into x of omega. X of t is converted to x of omega by using Fourier transform. Now I told you it is a band limited signal. Now we are applying Fourier transform to band limited signal. Now we are applying Fourier transform to band limited signal. Now we are getting the output is x of t is converted to x of omega. X of t is converted to x of omega. It is non-zero from minus omega m to plus omega m. It is non-zero from minus omega m to plus omega m. So once again I try to tell you. Wait. Here, whatever the continuous time signal I try to consider, whatever the wave shape. So I try to consider this is the continuous time signal, for example. Okay. Now I try to apply Fourier transform to this continuous time signal. The continuous time signal denoted by x of t with respect of t. We are applying Fourier transform to continuous time signal. Moreover, this continuous time signal is a band limited signal. Now it is used to get x of t is converted to x of omega. So that's why I told you it is a band limited signal. It is a limitation. It non-zero. It is non-zero from minus omega m to plus omega m. It is non-zero from minus omega m to plus omega m. It is non-zero from minus omega m to plus omega m. Before minus omega m, the value becomes to 0. After omega m, the value becomes 0. It is non-zero from minus omega m to plus omega m. Here, from minus plus omega m to minus omega m, it is non-zero. So otherwise, the value becomes to 0. This is the Fourier transform of any band limited continuous time signal. Okay. So what, sir, I try to consider this is a continuous time signal, sir. Now in this continuous time signal, it is a band limited signal. Now we are applying a Fourier transform. Now we are getting this output signal. Simple. Okay, this output signal means whatever the continuous time signal is there. Here we try to represent this continuous time signal is a band limited signal. Any continuous time band limited signal, we are applying a Fourier transform. Now we are getting x of omega with respect to frequency. It is non-zero from minus omega m to plus omega m. Anybody having any doubt? Are you understand? Anyone? Is it clear? Are you catching point? Right. Now, okay, okay, now, so we are considered once again. It is a continuous time signal. We are providing, sir. You always told me it is a sampler. The sampler, another name is called the multiplier. Simple. Okay, we are connecting to sampler or multiplier. It is used to generate the samples to turn on the switch here, to turn on the switch here. In between these two samples, the switch is in off. Okay, we are getting corresponding output is called as sampled output. XS of T, sampled output or discrete signal. Okay, now this continuous time signal is a band limited signal. It is a band limited signal. Now we are applying Fourier transform to this continuous band limited signal. We are getting the output is here. It is non-zero from minus omega m to plus omega m. It is non-zero from minus omega m to plus omega m. Okay, now listen carefully. I try to convey. Okay, now listen. We know sampling frequency means when f is greater than or equal to f or omega s greater than or equal to 2 omega m. 2 omega m. Okay. Now we know x of omega. X of omega means we are considering a continuous time signal. We are applying a Fourier transform. We are getting x of omega. It is non-zero from minus omega m to plus omega m. Okay. Now omega is greater than 2 omega m. Now first case, three cases are there. Omega is greater than 2 omega m or f is greater than 2 f. Right. In first case, whatever the waveform is there, it is omega m. It is minus omega m. Minus omega m. Now the same waveform is repeated again and again. Same waveform is repeated again and again. Okay, listen carefully. Here it is omega m. From here it is increasing, decreasing. It is one complete cycle. Minus omega m to plus omega m is one complete cycle. That is, it is increasing, decreasing. Now from zero onwards, it is decreasing. Now it is increasing. Now decrease and increase, it becomes to one complete cycle. That is called a sampling frequency. Okay, my intent is very simple, Amma. Increase, decrease. The combination of increase and decrease is called as one cycle. Now from zero onwards, I try to consider it is decreasing. Now it is increased. So increase, decrease. It is called as one time period, sampling period. Okay. Now it is omega m. It is omega s. What about this value? This value is less than the omega s, but greater than the omega m. So this value is omega s minus omega m. Omega s minus omega m. So here this value is omega s minus omega m. Omega s minus omega m here, omega s minus omega m greater than the omega m or less than the omega m? Greater than the omega m. Greater than the omega m. Okay, now omega s greater than omega m coming in this side, greater than 2. Okay, in this scenario, what will happen? The continuous time signals are original signals are repeated and again. These signals are not overlapped. These signals are not overlapped. The signals are not overlapped. The signals are not overlapped. So here our intention is very simple. The signals are not overlapped. Okay, that is the point number one. Okay, once again, I try to tell you, because without having proper idea, okay, the problem is entirely wrong. Okay, here I try to explain. Here, whatever the signal is there, here it is minus omega m, and it is plus omega m. Okay, from 0 onwards, it is decrease amma. Now it is having increase, increase one period. So that is called as omega s. Now in this period, I try to tell you omega s minus omega m, higher value minus lower value. In this point, omega s minus omega m we are getting here. Now this point is greater than the omega m here, greater than omega m. Now what we are getting here? We are getting omega s greater than 2 omega m. Okay, this is the first case. Second case. Here, the waveform is here. Same waveform is repeated. Now I told you it is omega m. It is decreased and increased. It is called as omega s. Now what about this point here? I tried to tell you omega s minus omega m. Now omega s minus omega m and omega m, those two are equal. Here in this point, those two are equal. Here is equal to. Now we are getting omega s is equal to 2 into omega m, 2 into omega m. Right? That is the second one. Third one. Here we are considered it is 0, it is omega m. Okay, it is omega s. Okay, now what about the value here? This value is called as omega s minus omega m. Now omega s minus omega m less than the omega m, less than the omega m, less than the omega m. Now omega s, omega m is coming that side, 2 omega m, 2 omega m. Okay, this scenario. So listen carefully. Here the signals are repeated without having overlap. For example, if you are try to make a call to your parents, at that time, some cases, okay, if you are there in call, so your call is connected to another number. So another person, unknown person is coming into our line. So speaking to something. So that means the call is overlapped. Similarly here also. Here the signal is separately is there. There is no overlapping is there. Overlapping is not there means it does not lose any information. So the original signal is recovered from the discrete signal without losing any information, without overlapping. Okay. Now second one. Here also signals are perfectly ended. Here it is ended. It is ended. Okay. Now here also the signals are perfectly repeated without overlapping. So here the signals are perfectly, original signals are recovered. But here one signal is going to end, before that one more signal is started. Now what will happen? In between this position, signals are overlapped. It lose some amount of information. So that's why according to our statement, omega s greater than 2 omega m, omega s is equal to omega m. In these two cases, under oversampling and a perfect sampling, the original signals are recovered from the discrete signal or sample output signal without losing any information or any data. Okay, but under sampling, the signals are overlapped. Means it loses some amount of information. So the sampling theorem is only verified during these two cases only. It is not verified for this condition. Okay, and moreover, I tried to tell you here. Okay, one more time. So whatever the waveform we are getting here, I try to consider. I try to take some space here. It is 0 only. It is omega m. Here it is called as omega s. What about this value here? This value is omega s minus omega m. Omega s minus omega m. It is omega s. It is omega m. Here this value is omega s minus omega. So omega s minus omega m are in terms of f or omega greater than omega m. So the condition is omega s greater than 2 omega. Okay, here the original signals are recovered. Okay, there is no overlapping is occurred. Okay, so the original signals are recovered. Our next to second one. Here these are x of omega. Okay, next. Here, the same waveform. End of here, I try to repeat it here. Continuously available. It is having some space is there. Some space is there. I told you what is the reason why the space is occurred. I told you, wait a second. Now here, it is omega m. It is 0 minus omega m. So now decrease, increase. Now it is called as omega s. What about this value? This value is called as omega s minus omega m. And omega s minus omega m and omega m, those two are equal. Those two are same values, is equal to omega m. So now omega s is equal to 2 omega m. 2 omega m. Right? Second one. Here in this case also, when the signals are perfectly landed, the original signals are recovered from the sampled output signal without overlapping. So the third one, here, the third one, last case, here. Before 100, one more signal started. Now here it is 0, it is omega m, it is omega s, it is called as omega s minus omega m. Now omega s minus omega m less than omega m, because omega m is there here, omega s minus m is there here. Now omega s less than 2 omega m. Okay, now what will happen? Signals are overlapped. Signals are overlapped, it loses some amount of information. So this effect is called as aliasing effect. Okay, so aliasing effect. This effect is called as aliasing effect. Okay, Nande? Now what we try to understand here. So we know that here, sir, what is the reason, sir? Here in between signal to signal, some space is there. What is the reason? It does not having any space. It means here we are using low pass filter. That is, here I try to sketch here. There are two low pass filters are there. Ideal low pass filter, practical low pass filter. Ideal low pass filter means it cuts sharply. It cuts sharply. From minus omega m to plus omega m, it cuts sharply. It does not allow it. Here we are using ideal low pass filter. So that's why it does not take any additional space. Okay. One more filter is there. It is ideal low pass filter. Low pass filter. Here it is called a practical low pass filter. In practical low pass filter, here, but it cuts here, but it does not cut sharply. It is having some extension is there. But actually it cuts here, but it does not cut sharply. It is having some additional value. That is practical. Okay. So because of the practical, it will take more space for that one. So this space is called as guard band. G-U-A-R-D. G-U-A-R-D. Guard band. This space is called as guard band. Okay. So I told you once again. Here in this scenario, first case, it is plus omega m, it is minus omega m. Okay, this is omega s. What about this value? Omega s minus omega m. Now omega s minus omega greater than omega m. So we are getting here. In this oversampling, the original signals are recovered. Okay. Now second one, here it is omega m, it is omega s. It is also be called as omega s minus omega m. Those two are equal here. In this scenario, same. It is omega m, it is omega s. It is called as omega m minus, sorry, omega s minus omega m. Okay, here this is the scenario. Here try to understand. Here when the signals are overlapped, here undersampling, when the signals are overlapped, when it loses some amount of information or data. When the signals are overlapped, it loses some amount of information or data. That effect is called as aliasing effect. Aliasing effect. Okay, aliasing effect. Okay, aliasing effect. Okay, aliasing. A-L-I-A-S-I-N-G. Aliasing effect. I told you here. Aliasing. aliasing effect. Okay, aliasing effect means moment of information. So this effect is called as aliasing effect. Here, the aliasing effect is occurred under sampling condition only. Under sampling condition only. And sir, these two are right. Sir, what is the reason? What is the reason why the space is occurred in between signal to signal? So what is the reason the space is not occurred? Anybody guess? ఈ వేవ్ ఫామ్ దగ్గర ఎందుకు సిగ్నల్ స్పేస్ వచ్చింది? ఈ వేవ్ ఫామ్ దగ్గర ఎందుకు స్పేస్ రాలేదు? ఎనీబడి గెస్? ఎనీవన్? Anyone? Under oversampling, we are getting whatever the waveform. In between waveform to waveform, okay, low pass filter, where we are using low pass filter. So we are using low pass filter. There are two low pass filters: ideal low pass filter, practical low pass filter. Where we are using ideal low pass filter, where we are using practical low pass filter. Anybody guess? Ideal low pass filter, practical low pass filter. I try to sketch here. Ideal means it cuts sharply and minus omega m2
f is equals to 2fm.
It cuts sharply.
Perfect sampling.
It is ideal low pass filter. Practical low pass filter means it will take some. Amma చెప్పండి, వాయిస్ కట్ అవుతుందమ్మా, మళ్ళీ చెప్పు. Amma, anyone? So just turn on your mics and respond. Anyone? Here there are two filters we are using: ideal low pass filter, practical low pass filter. Where we are using ideal low pass filter, where we are using practical low pass filter. Anyone? Anyone?
f is equals to 2fm దగ్గర ideal perfect sampling, sir.
Okay, f is equal. Okay, good. Okay.
f is greater than 2fm దగ్గర practical low pass filter, sir.
Good, Amma. So here the point is very simple. Okay, so that's why some space is occurred. So because here we are using practical low pass filter. It does not cut sharply. In practical low pass filter, it does not cut sharply. Okay, ideal low pass filter, it cuts sharply. Even though I try to here, see, it does not cut sharply. So here we are getting perfect waveform. But here we are not getting perfect waveform. So that's why some space is occurred. That space is called as guard band. That space is called as guard band. That space is called as guard band. Okay, even though I try to convey one point to you. Okay, ideal and practical. Okay, even though, for example, this class is this class or this lecture is delivered by myself as a human being. I try to cut this class sharply at 4 p.m. Actually, our time is 3 to 4 p.m. Okay, in ideal case, sharp 4 p.m. obviously the class is ended. That is ideal. But practical scenario, what will happen? I will take more than 4 or 5 minutes. Okay, that is a practical. But ideal case, it cuts sharply. Ideal case, it cuts sharply. Practical case, it will take some delay. It will take some delay. Because of this practical low pass filter, it will take some delay. Okay, that's why some space is occurred in between signal to signal. That space is called as guard band. That space is called as guard band. Anybody having any doubts? Anyone? Do you understand regarding to sampling theorem? This is the sampling theorem. Anybody? This is the 14 marks question, Amma. These waveforms are very, very important. In every point, we try to represent few points. Okay. Right. Amma, wait for 5 to 10 minutes. I try to complete this derivation part also. Okay, please wait few minutes, just 5 to 10 minutes only. I try to finish the topic. Okay, from tomorrow we try to start with a fresh topic. Okay, if anybody having any problem, if anyone, I need just 5 minutes, maybe more than 5 minutes. I try to finish this topic. If anybody having any objection, right? Now, so listen, simple. I try to convey simply. Listen carefully first. Here, listen, Amma. Because in this unit having only one derivation, if you are having this derivation, in every topic of this unit having same derivation, cut, copy, paste. Okay, right. Listen carefully. whatever the input we are providing, that is x of t. Listen carefully, x of t, right? It is called as sampler, that is called as del of t. Okay, this is called as xs of t, xs of t, or x of n, x of n. Listen carefully, because so whatever the derivation is there, this derivation is very very important role, because whatever the topics are there in this unit, all the topics are having same derivation. Okay, now here, according to the output, xs of t is equal to, what about the equation? Xs of t is equal to input into system, x of t into the system is called as del of t, input into system. Okay, this is equation number 1. This is equation number 1. Okay, here the input is x of t, here the system is del of t, the output is xs of t. Okay, output is equal to input into system, input into system. Here it is input, it is system, it is system, right? So we know that Fourier series, I try to consider exponential form of Fourier series, exponential form of Fourier series. I try to consider form of Fourier series had x of t is equal to sigma n is equal to minus infinity to infinity Cn e power minus Jn omega 1 by t integral of minus t by 2 to plus t by t x of t e power Jn omega st, Jn omega st. Here it is called as exponential form of Fourier series. This formula is very very important and very very required to us to finish this derivation, right? Now here I try to apply exponential form of Fourier series to impulse signal. I try to apply exponential form of Fourier series to impulse signal. Now wherever x of t is there in exponential form, x of t is replaced by del of t, because here we are applying Fourier series to impulse signal. Okay, now I try to change del of t is equal to the simple x of t is equal to del of t, sigma n is equal to minus infinity to infinity Cn e power minus j n omega st. Okay, now where Cn is equal to 1 by t integral of minus infinity to infinity, or sorry, minus t by 2 to plus t by 2. Okay, x of t is nothing but del of t e power jn omega st into dt. Here it is dt. Okay, okay, now here we are considered del of t value how much? Del of t value is 1
1,
and
sir.
del of t value is 1 when t equal to 0. When t equal to 0, del of t value is 0, t is not equal to 0, t is not equal to 0. Now here in this Cn value, in this Cn value, the formula is 1 by t. I already told you, first unit already we done some problems. No need to apply integral, no need to apply summation, because del of t value is 1 when t equal to 0. So what about the remaining portion? E power j n omega s t. In this portion, just we try to substitute t t equal to 0, t equal to 0. Exponential of 0 is nothing but 1. So Cn value is 1 by t. Cn value is 1 by t. Cn value is 1 by t. Okay. So here, when Cn we are getting, okay, sir, what is the reason why Cn value is 1 by t? I told you, integral of impulse into anything. Impulse value is 1 and t equal to 0. Now the remaining value, whatever the portion is there, in that portion put t equal to 0. So we are getting. Already we done this problem about the answer. So just 1-2 minutes and it's enough. Sigma n is equal to minus infinity to infinity. Cn value how much? 1 by t e power minus jn omega s into t. We are getting here. In del of t is substituted into this equation 2, substitute into equation 1. Okay, just x of t, del of t, xs of t. Xs of t is equal to x of t into del of t. Okay, according to exponential form of Fourier series. Here we are applying exponential form of Fourier series to impulse signal. So x of t is there, x of t is replaced by del of t. Now we are getting here. So no need to apply integral, no need to apply summation when the impulse signal is there. So we are getting Cn. Now we are getting del of t value. This del of t value substituted in equation number 1. Okay, here story is done. So this is equation number 1. This is called as exponential form of Fourier series. Okay, here this is exponential form Fourier series. When del of t is equal to 1 for t equal to 0, so the value becomes to 1 by t. Okay, now we are substituting 1 by t into here. We are getting del of t is equal to. Now this del of t is substituted. This del of t is substituted into equation number 1 here. Equation number 1. Now we are getting here. So I try to convey one point to you. Here in x of t, I try to apply Fourier transform. We are getting x of t into x of omega. In x of t, in Fourier transform, one of the properties there, that is complex property. N omega st. What about the property here? This is called as a complex property, complex frequency of Fourier transform. Okay, now we are getting x of t becomes to x of omega. What about the remaining value? N omega s. N omega s. So minus n into omega s. Okay, x of t ki Fourier transform apply we are getting x of omega. X of t exponential of e power j n omega st ki Fourier transform apply we are getting x of omega minus n omega s. Okay, now we are applying Fourier transform. We are getting x of t becomes to xs of omega. Okay, x of t e power j n omega s becomes to x of omega minus n omega s. Okay, here this is the derivation. It's enough. Okay, as per your convenience, omega is also replaced by f. Simple. So this is the final. Anybody having any doubts? Anyone? Anyone having any doubts? It related to derivation and do you understand? Is it clear? Is it clear? Do you understand? So I told you this derivation is very, very important. I'll have to be prepared because in this unit, whatever the topic is there, that same derivation just cut, copy, paste. Okay, right, Amma. Right. One more point is so these are the applications of sampling theorem. So these are used for speak recognition systems, even though our phone calls, and moreover radar stations, okay, radio navigation systems. Okay, so radar stations means even though we are getting whatever the tufans, whatever the weather conditions report we are getting, so those are recognized by one station that is called as radar station. So in nearer of Eluru, in Machilipatnam, one of the radar station is there. Okay, so that is radar station purpose. Okay, so these are the simple things for music recording purpose or speech recognition purpose. Okay, in the movies or biometric. So all these purpose, this is the best application for sampling theorem. Okay, right. So one more definition is there. So I told you when fs greater than 2fm, oversampling and when fs equal to 2fm, it is called as critical sampling. Critical sampling. When the sampling frequency is equal to twice of the fundamental frequency. Here we have observed different waveforms. In between waveform to waveform, some space is there. That is called as guard band. This space is occurred in here. But in perfect sampling, in waveform to waveform, it does not having any space. Here we are using ideal low pass filter. Here we are using practical low pass filter. Practical, ideal. So here when fs is equal to fm, is called as Nyquist rate of sampling. Nyquist rate of sampling. Fs is equal to 2fm. Okay, when the sampling frequency is equal to twice of the fundamental frequency is called as Nyquist rate of sampling. This formula is very, very important for our problematic part also. Okay, so up to till now I tried to cover this portion. If anybody having any doubts, feel free to ask me. Anyone? Do you understand up to till now? Up to till now, anybody having any doubts? Right, Amma? Okay, so tomorrow, whatever the remaining portion is there, we will meet on tomorrow's session. Okay, so my request is, please. So at the time of in this revision session also, so even though in every day, please, all of you, please go through the material, whatever the session we try to revise. So all of you be prepared. If anybody having any doubts from the next class, so feel free to ask me. Okay, without practice, without having proper confirmation on this subject is typical when compared to all the remaining subjects. Okay, thank you one and all.